Deep within the crowded heart of our galaxy, shrouded by impenetrable walls of dust and gas, a silent giant rests in the absolute dark. It is invisible, yet its immense gravity guides the orbits of hundreds of billions of stars in a slow, perpetual dance that has continued for eons. This is Sagittarius A, the supermassive black hole at the center of the Milky Way, a place where the rules of space and time bend under the weight of 4 million suns. As we prepare to journey into this quiet cosmic void together, please take a moment to subscribe to the channel, support these peaceful explorations, and leave a like if you find comfort in the stars. Wherever you are listening from tonight, whether you are resting in a quiet room or looking out at the night sky from some distant corner of the world, please feel free to share your location and local time in the comments below. Close your eyes if you wish, letting the soft voice guide you into the stillness of space. For now, let the weight of the day fade away. Dim your lights, and find a comfortable position as you settle into a gentle, natural rhythm of breathing, allowing any tension in your shoulders and mind to dissolve. There is no need to rush, and no need to remember every detail of the cosmic science we will encounter. Simply let the atmosphere of the galactic center wash over you. The universe is vast, and its mysteries unfold slowly, without rush. Let us leave the familiar warmth of Earth behind, allowing the mind to drift deep into the core of our galaxy, where millions of stars crowd together in a brilliant display of light. Leaving the quiet, dark suburbs of the solar system, past the icy reaches of the Oort cloud where the sun's gravitational hold is a mere whisper and stars are scattered like lonely beacons across light years of cold, empty space. The density of the cosmos begins to shift in a slow, magnificent progression. As the journey proceeds deeper toward the center of the Milky Way, crossing the wide spiral arms where interstellar gas and dust gather to build the nurseries of future suns, the empty silence starts to give way to a steady gathering of light. In the local neighborhood of the galaxy, the distance between stars is vast and silent, a quiet expanse where the nearest stellar neighbor is more than 40 trillion kilometers away, requiring years for even a beam of light to cross the void. But as the core approaches, this isolation dissolves, and the spaces between the stars begin to contract. The stars draw closer together, their numbers multiplying with every light year traversed, until the background darkness is filled with a dense, shimmering fog of starlight. At the very heart of this system, within a central nuclear cluster only a few light years across, millions of stars reside in close proximity, packed into a tight stellar city that would normally hold only a single family of planets in our part of the galaxy. The sheer density of this stellar metropolis is almost beyond comprehension, representing a concentration of matter that is 1,000,000 times greater than anything experienced in the quiet suburbs around the sun, transforming the galactic core into a brilliant, crowded hub of stellar life. If a world were to exist near this galactic center, orbiting one of these crowded suns within the nuclear star cluster, the night sky would bear no resemblance to the quiet, dark canopy observed from the surface of Earth. Instead of a few thousand pinpricks of light scattered across a dark dome, the sky would be ablaze with millions of stellar neighbors, some shining with the brilliance of full moons and casting a warm, constant glow across the landscape. The night would never truly arrive on such a world. The sky would remain a luminous, shifting tapestry of silver, electric blue, and deep amber, bright enough that any object on the surface of this planet would cast soft, overlapping shadows pointing in multiple directions, created by the light of 1,000 different suns. The collective glow of these millions of stars would illuminate the landscape, creating a perpetual twilight, where the quiet of darkness is entirely replaced by the comforting presence of light, and the stars appear as large, radiant disks rather than tiny points. Yet, despite this overwhelming brightness and the proximity of so many stellar engines, there is a profound silence to the scene. The stars move in their orbits without a sound, gliding through the thin, ionized gas of the core like silent ships on a crowded ocean, their paths intersecting in a silent ballet of light that plays out across the sky for millions of years. This crowded environment creates a complex, shifting web of gravitational forces that shapes the destiny of every stellar body within its reach. In the quiet, lonely corner of the galaxy where our solar system resides, stars rarely influence one another directly, their orbital paths remaining stable and undisturbed for billions of years without the threat of perturbation. But here, in the dense heart of the Milky Way, stellar encounters are a common occurrence, happening on timescales of thousands rather than billions of years. Suns pass close to one another, their gravitational fields overlapping and gently tugging at their outer atmospheres, sometimes stripping away gas or cosmic dust in the process. These close passages can permanently alter the paths of the stars, turning orderly, circular orbits into long, stretched ellipses that swing wild and deep through the central cluster, bringing the stars close to the central black hole before flinging them back out to the edges of the core. For any planets that might attempt to form in these crowded systems, the environment is incredibly hostile and volatile. The constant gravitational disruptions from passing stars make it difficult for protoplanetary disks of dust and gas to remain stable long enough for planets to coalesce and grow. If a world does manage to form against these odds, its orbit is perpetually perturbed, destined to be pulled and shifted by the collective gravity of 1,000 neighboring suns, preventing the long-term climate stability necessary for the development of complex systems. The calm stability taken for granted in our solar system is replaced by a dynamic, ever-changing dance of gravitational alignment, where every orbit is a temporary compromise between competing pulls. The composition of this central stellar population is equally remarkable, reflecting the rich history of star formation in the core. The core is not merely crowded. It is a diverse and colorful assembly of stellar life in all its evolutionary stages, showing both the beginning and the end of stellar cycles. Massive, hot, blue stars, belonging to clusters like the arches and the quintuplet, burn with intense heat and light, their lifespans short and brilliant, lasting only a few million years compared to the long, slow lives of the red dwarfs that will endure for trillions of years. These young giants, some of the most massive stars known, pour out torrents of ultraviolet radiation and powerful stellar winds, illuminating the surrounding gas clouds and creating glowing nebulae that drift through the crowded space like cosmic clouds of purple and magenta. Alongside these short-lived giants are ancient red giants, stars that have exhausted their core hydrogen and swollen to hundreds of times their original size, their cool, outer atmospheres glowing with a deep crimson light as they slowly shed their mass into the interstellar medium. There are also the dense, invisible remnants of dead stars, white dwarfs, neutron stars, and stellar mass black holes silently drifting through the crowd, their presence felt only when their gravity temporarily bends the light of a background star or pulls gas from a passing neighbor. This mixture of the young and the old, the blindingly bright and the dark and dead, creates a rich cosmic tapestry of stellar diversity, all bound together by the central gravity of the galaxy. To peer into this crowded core from the vantage point of Earth requires looking through a dense, dusty shroud of interstellar dust and gas that lies along the galactic plane. This cosmic dust, composed of tiny particles of carbon, silicates, and ice grains, acts as a thick fog that absorbs and scatters visible light, blocking our view of the galactic center. If observers were to rely only on human eyes or optical telescopes, the center of the galaxy would appear as a dark, empty patch in the night sky, completely hidden behind the dark rift of the Milky Way. For generations, astronomers could only wonder what lay beyond this dark curtain, imagining either a void or a dense cluster of stars but unable to prove their theories. It was only with the development of infrared and radio astronomy in the 20th century that observations began to see through the dust fog. Infrared light, with its longer wavelengths, it can pass through the small dust particles without being scattered, much like infrared cameras can see through smoke, revealing the crowded stellar city that lies behind the shroud. Radio waves, longer still, travel unimpeded, across the 26,000 light-years of space between Earth and the core, bringing crucial data about the motions of gas, the magnetic fields that thread through the crowded space, and the high-energy processes occurring near the central black hole. What was once an impenetrable mystery hidden in darkness has become one of the most studied and active regions in the entire cosmos, observed by global networks of telescopes. As this crowded heart of the galaxy is contemplated, the realization grows that the center of the Milky Way is not a cold, empty void, but a place of immense vitality, movement, and light. The millions of stars that gather here are not drifting randomly, but are all participating in a grand, coordinated movement, their individual paths shaped by the invisible mass that sits at the very center of the system. They orbit in a giant, swirling swarm, a collective entity that represents the gravitational anchor of the Milky Way, holding the entire spiral structure together. In the grand scale of the universe, this crowded core is a testament to the power of gravity to organize and concentrate matter, creating environments of extreme density, energy, and light that challenge our understanding of what a stable world can be. Yet, even in its crowded and complex nature, the core remains a place of quiet majesty, far removed from the chaotic noise of human life, where the orbits of millions of suns proceed with a calm, slow regularity, tracing out their paths over eons. This is a cosmic clockwork that has been ticking for billions of years and will continue to tick long after the stars in the outer suburbs have grown cold, a quiet monument to the ordering principles of the universe, rising far above and below the flat, crowded plain of the Milky Way, where the stellar density rapidly drops and the stars thin out into the cold halo of the galaxy. There exists a pair of silent monuments to its active and energetic past. For billions of years, the space directly above and below the galactic center appeared to be nothing more than an empty, dark void, a quiet region of space devoid of any remarkable features or emissions. But in the early years of the 21st century, in the year 2010, observations from space-based observatories revealed that this apparent emptiness is actually occupied by two colossal, balloon-like structures of energy that had remained hidden from human knowledge. Rising like giant, symmetrical lobes of purple light, these structures stretch for 25,000 light-years in both directions, extending nearly half the width of the entire galactic disk out into the intergalactic medium, forming an hourglass shape centered on the core. Astronomers call them the Fermi Bubbles, named after the Fermi Gamma-ray space telescope launched by NASA that first detected their faint, high-energy signature. This space telescope, equipped with sensitive detectors designed to capture high-energy photons, revealed that the bubbles extend symmetrically, forming a massive hourglass structure that is centered on the galactic core. These bubbles are completely invisible to human eyes, hidden from our optical telescopes, yet they glow softly in the highest frequencies of light, casting a ghostly, silent radiance across the northern and southern skies of our galaxy, mapping out the shape of an ancient cosmic event that reshaped the halo. If these colossal structures were somehow visible to an observer looking up from the surface of Earth, the night sky would be dominated by two towering, violet clouds of energy rising from the galactic horizon and stretching across more than half of the visible dome of stars, spanning the heavens like giant cosmic wings. They would dwarf the constellations, hanging in the dark like giant, glowing nebulae that span the sky from north to south. Yet, despite their immense scale, the interior of these bubbles is incredibly sparse and rarefied. They are filled with a hot, thin, ionized gas that is expanding outward at millions of kilometers per hour, carrying high-energy particles away from the galactic center. This gas is so diffused that it represents a near-perfect vacuum, far emptier than any gas nebula found in the galactic plane, containing only a few atoms per cubic meter of space. Within this vast void, high-energy cosmic rays, including protons and electrons, move at close to the speed of light, guided by weak, parallel magnetic fields that thread through the expanding lobes and shape their boundaries. The gas inside is heated to temperatures of millions of degrees, yet it is so sparse that it would feel like a cold void to any physical explorer. High-energy electrons spiraling around the magnetic field lines emit synchrotron radiation, which is what telescopes detect across the radio spectrum. The bubbles are a study in cosmic contrast, immense in scale and volume, yet nearly empty in substance, carrying the kinetic and thermal energy of a forgotten epoch out into the cold spaces between the galaxies. The creation of these energetic colossi points to a time when the galactic center was a very different, far more active environment than what is observed today. Today, Sagittarius A rests in a quiet, dormant state, consuming only tiny, sporadic amounts of nearby gas and stellar winds. But the presence of these bubbles indicates that this current stillness is merely a temporary phase in a much larger, repeating cycle of activity. Approximately 6 million years ago, a massive influx of gas and dust must have fallen toward the central black hole, triggering a period of intense, rapid feeding that released unimaginable energy. As this gas spiraled into the event horizon, it became heated to billions of degrees, generating powerful winds of radiation and relativistic particles that were funneled outward along the spin axis of the black hole. Perpendicular to the galactic plane, this jet-like outflow, moving at a significant fraction of the speed of light, pushed through the surrounding dense gas of the galactic disk, carving out the two giant cavities in the galactic halo that now tower over the galaxy. The bubbles are the quiet, fading echoes of this ancient eruption, acting as silent witnesses to the raw power that once radiated from the center of the Milky Way, shaping its structure. Astronomers estimate that this event released as much energy as 100,000 supernovae exploding simultaneously, a burst of energy that would have been bright enough to light up the night skies of neighboring galaxies. Peering into the complex physics of these structures, researchers have discovered that they are not static clouds of gas, but dynamic, evolving systems that interact with the surrounding space. The edges of the bubbles are marked by sharp, well-defined shock fronts, where the outward-moving gas collides with the colder, denser material of the galactic halo, creating a boundary layer of high pressure. At these boundaries, shock acceleration processes push particles to extreme energy levels, producing the high-frequency gamma-ray emission that first revealed the bubble's existence to the Fermi telescope. The gas inside the bubbles is also a source of X-rays, glowing with a soft, thermal warmth that has been measured by space observatories like Chandra and Erosida, revealing the high temperatures of the gas. In recent years, observations using the Hubble Space Telescope have studied the ultraviolet light of distant, bright quasars as it passes through the bubbles on its way to Earth, analyzing how the gas absorbs different wavelengths of light. By looking at the absorption features in the light of dozens of quasars, researchers have mapped the boundaries of the wind, showing that it moves at speeds of up to 1,000 kilometers per second, pushing a shockwave through the galactic halo. This absorption spectroscopy has allowed astronomers to map the velocity, density, and chemical composition of the material, showing that the bubbles contain heavy elements like carbon, silicon, and aluminum, proving they are still expanding and carrying the chemical remnants of the galactic core out into the deep halo, enriching the surrounding space. The role of these bubbles in the overall life and evolution of the galaxy is profound and far-reaching. The immense energy they carry is not lost to space. It actively shapes the environment of the Milky Way and determines its long-term future. As the hot gas expands into the halo, it heats the surrounding circumgalactic material, preventing it from cooling and falling back onto the galactic disk as cold gas clouds. This process, known as active galactic feedback, is essential for regulating the rate of star formation in the galaxy over geological timescales, acting as a brake on the galaxy's growth. Without these periodic outflows to heat the halo gas and blow it away, the disk of the Milky Way would consume its gas reservoirs much faster, leading to a rapid, unsustainable burst of star formation, followed by an early, permanent quietness as the fuel ran dry. by blowing away the raw material of new stars. The central supermassive black hole acts as a cosmic regulator, ensuring that the galaxy grows, forms stars, and evolves at a steady, sustainable pace over billions of years. This feedback mechanism is a common feature in many galaxies across the universe, showing that supermassive black holes play a key role in the life cycle of their hosts. The Fermi Bubbles are the closest example of this process, allowing astronomers to study its physics in detail. The bubbles are the visible, energetic manifestation of this regulatory mechanism, a giant system of thermal control that spans tens of thousands of light years. In the vast timeline of the cosmos, the Fermi Bubbles are a reminder of the impermanence of the astronomical structures observed. The quiet, peaceful galaxy inhabited today is only a single frame in a long, dynamic history of changes and eruptions. The bubbles will continue to expand, their boundaries slowly fading as they mix with the intergalactic medium, until their energy is completely dispersed into the intergalactic void. Eventually, over millions of years, the hot gas will cool and new gas clouds will gather in the core, drawn in by gravity, perhaps triggering another cycle of accretion and another major eruption that will blow new bubbles of energy into the dark. As the night sky is observed from our quiet corner, there is a deep comfort in knowing that the silence of the cosmos is not a sign of inactivity or decay, but rather the quiet breathing of a living, breathing galactic system where the monuments of past eruptions stand silent and immense in the dark, waiting for the next cycle of stellar light to begin, and continuing their slow, majestic expansion into the unknown. The cycle of accretion, eruption, and quietness is a fundamental rhythm of the cosmos, a slow pulse that plays out over hundreds of millions of years. As the bubbles expand and fade, they carry the memory of the galaxy's active past into the deep future, a testament to the ongoing evolution of the Milky Way. Drifting deeper still into the crowded core of the galaxy, past the dense stellar clusters and gas lanes, the stars begin to exhibit a behavior that challenges the very nature of planetary stability and orbit mechanics. In the outermost regions of the Milky Way, including the neighborhood of our solar system, stars move with a slow, stately majesty, taking hundreds of millions of years to complete a single circuit around the distant galactic center. But as the distance to the central supermassive black hole shrinks to only a few light hours or light days, the cosmic choreography accelerates into a silent, hyperspeed dance of light and gravity. This is the domain of the S-stars, a cluster of unique, massive stellar bodies that orbit the invisible gravity of Sagittarius A in tight, highly elliptical, and random paths, resembling a swarm of bees buzzing around a hidden hive. Among them, a star known as S2 or S0-2 acts as a guiding light, a bright, massive blue-white sun that has been tracked by astronomers for over 3 decades. It moves like a silent pendulum in the absolute dark, swinging far out into the crowded stellar field before diving deep toward the dark center, executing a cosmic loop that takes approximately 16 Earth years to complete, providing a perfect clock to measure the warped spacetime. This continuous tracking has allowed scientists to construct a highly detailed map of the gravitational potential, showing that the central gravitational field is remarkably clean and free of significant perturbing objects, which allows for extremely precise tests of orbital mechanics. The observation of these stars represents one of the most patient and precise achievements in modern observational astronomy. For decades, the exact nature of the center of the galaxy was a deep mystery, hidden behind the impenetrable dust clouds of the galactic plane. In the final years of the 20th century, 2 independent teams of astronomers, using the largest telescopes in Chile and Hawaii, began to track the positions of these individual stars. One team, led by Reinhard Genzel, utilized the telescopes of the VLT in Chile, while another team, led by Andrea Ghez, used the Keck Observatory in Hawaii. They had to develop new techniques to overcome the blurring effects of Earth's atmosphere, first using speckle interferometry, and later developing advanced adaptive optics systems. Adaptive optics works by projecting a powerful sodium laser beam into the upper atmosphere to create a fake guide star. Sensors then measure the atmospheric turbulence, and deformable mirrors adjust their shapes hundreds of times per second to correct the image in real time. Year after year, they photographed the central cluster in the infrared spectrum, measuring the positions of the stars with millisecond precision. What they saw was a revelation that transformed astrophysics. The stars were not drifting randomly. They were orbiting a single, invisible point of gravity. As S2 approached this point, its speed increased dramatically, tracing a perfect Keplerian orbit that proved beyond doubt that a massive, compact object sat at the center of the Milky Way, guiding every stellar path. This patient, decades-long work reached a historic milestone in the year 2020, when the leaders of these research teams were awarded the Nobel Prize in Physics for the discovery of a supermassive compact object at the galactic center. By carefully tracking S2 through a full 16-year orbit, they were able to calculate the mass of the central object with unprecedented accuracy, establishing that 4.3 million solar masses were concentrated into a region smaller than the solar system, confirming it was a supermassive black hole. S2 makes its closest approach to the black hole at a distance of only 17 light hours, a distance equivalent to 3 times the orbit of Pluto, zipping past the event horizon. For instance, S2 has a spectral type of B-type main sequence star, meaning it is about 15 times more massive than the Sun and glows with intense blue light. Tracking it requires tracking the motion of its hydrogen absorption lines as they shift back and forth. At this closest point, S2 reaches an astonishing velocity of 7,600 kilometers per second, which is nearly 3% of the speed of light. At such extreme speeds, the classical physics of Isaac Newton is no longer sufficient to describe the stellar motion. The star enters a realm where Albert Einstein's theory of general relativity must be used to calculate its path, a place where gravity bends not only the path of the star but the passage of time itself, causing time to dilate for the star relative to observers on Earth who watch the stellar clock slow down in the intense gravitational well of the central giant. As technology and telescope sensitivity improved, even more extreme members of the S-star family were discovered closer to the black hole. In the years following 2020, astronomers using the VLT identified stars that orbit even closer and move far faster than S2. A star designated S29 was tracked moving at over 8,000 kilometers per second during its closest approach to the black hole. Another star, S62, was discovered orbiting the central mass in just 9.9 years. More remarkable still was the discovery of S4714, a star that exists on an even more extreme trajectory. S4714 zips around Sagittarius A in an orbit that brings it within only 12.5 light hours of the event horizon, which is closer than any other known star. At its point of closest approach, the velocity of S4714 reaches an astonishing 24,000 kilometers per second, which is approximately 8% of the speed of light, a speed that would carry it around the entire Earth in less than 2 seconds. At this speed, relativistic effects are prominent and measurable. Time dilation causes the internal processes of the star, including its light emissions, to run slightly slower relative to an observer far away, and the physical shape of the star is subjected to immense gravitational tidal forces that test the limits of stellar structure and threaten to tear it apart, squeezing the stellar core with immense pressure during each passage. These extreme orbits serve as a unique, natural laboratory for testing the most fundamental laws of physics under conditions that cannot be replicated on Earth. As S2 and other stars, like S4714, dive close to Sagittarius A, they experience a physical phenomenon known as gravitational redshift, a direct consequence of general relativity. The immense gravity of the supermassive black hole pulls at the electromagnetic waves emitted by the stars, stretching the photons to longer, redder wavelengths as they climb out of the deep gravitational well. This redshift was measured with extreme precision during S2's closest passage in the year 2018, using instruments on the VLT, matching the predictions of general relativity perfectly. Furthermore, the orbits of these stars do not remain fixed in space. Instead of tracing the same closed ellipse repeatedly, the orbits precess, meaning the entire ellipse rotates slowly over time, drawing a rosette or flower-like pattern in space due to the warping of spacetime caused by the black hole's mass. This precession can only be measured because astronomers have tracked S2 for multiple complete orbits, observing how the closest approach point shifts in space by a small fraction of a degree each time it completes its 16-year cycle. This relativistic precession, known as the Schwarzschild precession, was also confirmed through observations of S2, providing another triumph for Einstein's theories in the strongest gravitational field ever tested, demonstrating that spacetime is indeed a dynamic and malleable fabric. The existence of these stars, so close to the event horizon, remains a source of scientific wonder and debate. They are young, massive stars, which means they must have formed recently. Yet the extreme tidal forces of the black hole should have prevented the cold molecular gas clouds from collapsing to form stars in this region. This paradox, known in astrophysics as the paradox of youth, suggests that the S-stars may have migrated from farther out in the galaxy, where star formation is easier, or perhaps they formed within a dense, temporary disk of gas that once surrounded the black hole and shielded them from tidal disruption. Another theory suggests the Hills mechanism, where a binary star system wandered too close to the black hole, causing one star to be captured into a tight orbit, while the other was ejected from the galaxy at high speed as a hypervelocity star. These stars provide a key to understanding the galactic environment, showing how matter can survive and adapt in close proximity to a gravitational void. As they continue their silent, high-speed orbits through the vacuum, they carry the secrets of their origin and the nature of gravity itself. The dance of the S-stars is a quiet testament to the mathematical order that underlies the most extreme environments in the universe, a beautiful, repeating pattern of motion that continues to unfold in the absolute dark of the galactic center, proceeding in perfect harmony. This orbital choreography continues silently through the eons, a clockwork system that reminds us of the persistent stability of gravitational laws, even at the edge of the ultimate void. Deep within the warm infrared glow of the galactic center, hidden behind the thick dust lanes of the Milky Way, drift unique astronomical objects that seem to defy simple classification, moving through the turbulent dust lanes like silent, glowing spirits of gas and dust. In the early years of the 21st century, as advanced telescopes and infrared detectors mapped the central region of the Milky Way in ever greater detail, astronomers noticed several faint, elongated blobs of red-hot material that behaved in unexpected ways. These mysterious blobs did not have the sharp, clear edges of normal stars, nor did they have the diffuse, spreading structures of typical gas clouds that are easily deformed. Instead, they appeared as soft, smoky envelopes of gas and dust, gliding along highly elliptical orbits around the supermassive black hole. Sagittarius A scientists labeled them the G objects, a unique class of astronomical bodies that have only been found in the extreme, high-gravity environment of the galactic core. Today, at least 6 of these objects are officially catalogued, labeled G1 through G6, with G1 first identified in the year 2004 and G2 in 2011, each one tracing a distinct and challenging path through the gravitational field of the central giant, swinging close to the horizon before escaping back into the outer core. These objects represent a major puzzle because their outer gaseous sheaths are so large and tenuous that they should be easily stripped by the gravity of the central giant. For many years, the true physical nature of these G objects was the subject of intense, ongoing debate among astrophysicists worldwide, dividing the scientific community into two main camps. A simple, unstructured cloud of gas and dust, when exposed to the intense gravitational tidal forces near a supermassive black hole, should be violently stretched, sheared, and torn apart, its material quickly stripped away and pulled into the glowing accretion disk, leaving nothing behind. When the object known as G2 was first discovered in 2011 by astronomers in Germany, observations showed it was on a trajectory that would bring it incredibly close to Sagittarius A in the spring of 2014. Many researchers anticipated a spectacular show of cosmic feeding, predicting that the fragile gas cloud would be completely disrupted, shredded, and consumed by the gravity of the black hole, causing a major, bright flare of X-ray and infrared activity at the galactic center. Telescopes around the world, from the massive twin telescopes on the mountaintop of Mauna Kea in Hawaii to the orbiting space observatories, were pointed toward the core, waiting to witness the destruction and consumption of this fragile traveler, preparing to record every millisecond of the event. The expectation was that G2 would become a simple snack for the sleeping giant, offering a rare opportunity to watch the accretion process in action. But when G2 made its closest approach, known as the Precession passage, in the spring of 2014, the universe chose to surprise those who were watching and challenge their models, showing that nature is often more resilient than predicted. As the object swung around the supermassive black hole at a distance of only 36 light-hours, which is about 300 times the distance from Earth to the Sun, it did indeed stretch under the gravity, turning into a long, thin, trailing filament of gas and dust that spanned billions of kilometers. Yet, to the surprise of many, it did not break apart or dissolve entirely into the accretion disk. Instead, as it rounded the point of closest approach and began to move away along its orbit, the object managed to keep its compact core intact and pull its stretched envelope of gas back together, continuing its journey. This remarkable survival proved that G2 was not a simple, passive gas cloud, but something much more substantial, containing a compact, heavy source of gravity at its core, such as a star, that was strong enough to hold the surrounding dust and gas together against the immense, ripping tidal forces of the black hole, resisting the pull of the gravity, and proving that a hidden anchor was shielding the cloud. The leading scientific theory today suggests that G2, and indeed all the other G objects, are actually young stars that are surrounded by thick, warm shells of interstellar dust and gas. These are not ordinary suns, but likely binary star systems, consisting of two stars orbiting a common center that have been forced to merge under the intense gravitational influence of the central supermassive black hole. In the crowded, high-gravity center of the galaxy, the tidal forces of Sagittarius A can disturb the orbits of binary stars through a process called Kozai-Leidov oscillations, causing their mutual orbit to become highly eccentric and forcing the two stars to draw closer and closer together until they eventually collide and merge into a single, larger star. This merger is a slow, complex process that throws off a massive cloud of dust and gas, which remains gravitationally bound to the newly formed star, creating the soft, smoky, and elongated appearance observed by our infrared telescopes. This merged star is still settling down, bloated and glowing in the infrared spectrum as it slowly radiates away the energy of the collision. The thick cocoon of dust acts as a protective shield, absorbing the intense ultraviolet and X-ray radiation that fills the galactic center, protecting the star within from being stripped of its outer layers by the strong stellar winds of neighboring giants, allowing it to survive in the core. Understanding these G objects has allowed astronomers to paint a much more detailed and accurate picture of how stars evolve and interact in the most extreme environments of the universe, where gravity rules. The G objects are not permanent, stable structures. They represent a temporary, transitional phase in the lives of merged binary stars that lasts for only a few million years. Over time, the surrounding dust and gas envelope will slowly disperse, blown away by the merged star's own stellar winds, and the intense ionizing radiation of the central black hole, eventually revealing the bright, young star that lies hidden within the dark shroud. Until then, they remain as mysterious cocoons, hiding their stellar interiors from direct view, detectable only through the warm infrared radiation emitted by their dusty shells. The survival of G2 during its closest passage in 2014 demonstrated that even in the immediate vicinity of a supermassive black hole, where gravity is strong enough to warp spacetime and tear gas clouds apart, compact stellar structures can maintain their integrity and persist in their orbits, challenging previous assumptions about the destructive nature of supermassive black holes and showing that stars can endure in the harshest environments. The G objects are a quiet reminder of the resilience of structure and gravity in the cosmos, proving that order can survive in the midst of chaos. In a hostile environment dominated by a central supermassive black hole that seeks to rip everything apart, these dusty travelers continue their silent, elliptical journeys, drawing close to the edge of the void and returning intact. They show that the galactic center is not merely a place of destruction and consumption, but also a place of stellar transformation and rebirth, where binary stars are merged and reborn inside protective cocoons of dust. As they glide through the dark, they carry the history of their stellar parentage, the memory of their close collision, and the quiet strength of the gravity that holds them together, moving in perfect harmony with the millions of other stars that dance around the dark heart of the Milky Way, maintaining their orbits through the eons and enriching our understanding of stellar dynamics under the influence of Sagittarius A. Their continuing presence indicates that the core is a nursery of new star types, born from the remnants of older systems. These dusty objects offer a glimpse into the future of our galaxy, where stars will continue to interact, merge, and evolve, guided by the unseen gravity of the central giant, spinning silently in the cosmic dark. This persistence is a beautiful example of how nature finds a way to preserve stellar structures, shielding them within warm envelopes of dust and allowing them to trace their paths undisturbed through the gravitational turbulence of the galactic core. Beyond the physical matter of the crowded stars and the dark dust lanes of the galactic center, the very light that travels through this region becomes a subject of extreme cosmic distortion and warping. Light is the fastest entity in the universe, moving through the cold vacuum of space at nearly 300,000 kilometers per second, tracing out what should be straight lines across the cosmos. Yet, when it approaches the immense gravity of the supermassive black hole Sagittarius A, its straight, orderly path is bent and warped like water flowing around a smooth stone in a rapid stream. This physical phenomenon, known as gravitational lensing, creates a shimmering, watery, and fluid distortion in the background starfield, transforming the space directly around the black hole into a giant, natural magnifying lens. This lensing is similar to looking through the base of a wine glass, where background shapes are stretched into arcs. As photons from distant, background stars and galaxies pass near the outer boundary of the event horizon, they are deflected by the warped spacetime, arriving at our telescopes on Earth along curved and stretched paths that mask their true origin in the cosmic dark, making stars appear in places they do not actually occupy, creating a complex mirage. The physical foundation for understanding this optical phenomenon was laid over 100 years ago by Albert Einstein in his general theory of relativity, which replaced the classical Newtonian concept of gravity. Einstein proposed that gravity is not a physical force that pulls on mass across space, but rather the geometric warping of the fabric of space-time itself caused by mass and energy. A massive object, like the 4 million solar masses of Sagittarius A, creates a deep, steep depression in this four-dimensional fabric, much like a heavy lead sphere resting on a stretched, flexible sheet of fabric. Light, which always travels along the shortest path, or geodesic, through spacetime, must follow the warped contours of this sheet. When a distant background star aligns perfectly behind the black hole from the perspective of observers on Earth, its light is bent symmetrically around the central mass. The size of this ring is directly proportional to the mass of the black hole, making it a valuable tool to measure its physical dimensions from afar. Instead of appearing as a single, faint point of light, the lensed star is stretched into a luminous, glowing, and perfect circle of light, known as an Einstein ring, framing the absolute darkness of the black hole's shadow in a brilliant halo of starlight, showing the shape of warped spacetime. If the alignment of the background star is slightly off-center relative to the observer and the lens, the gravitational lensing effect becomes even more complex, splitting the light of a single sun into multiple, separate stellar images. An observer using high-resolution telescopes would see 2, 3, or even 4 distinct points of light surrounding the black hole, all originating from the exact same background star. These ghost stars appear to float in the dark, their positions slowly shifting and dancing as the background star moves relative to the gravitational lens, creating a cosmic illusion. Because the curved paths the light waves travel around the black hole are of different physical lengths, the light arriving from one side of the gravitational well may take longer to reach Earth than the light traveling along the other side. This gravitational time delay, first predicted by Erwin Shapiro, means that the different paths act as different lanes in a cosmic race, where the curvature of the lane determines the arrival time. This creates a measurable time delay between the different images, meaning astronomers observing a sudden flare in one of the lensed images might see the same flare repeat in another lensed image, days, weeks, or even months later, providing a unique and highly accurate method to measure the geometry of space-time and the expansion rate of the universe, tracking the pulse of the stars. This gravitational lensing is not merely a visual curiosity or an optical illusion. It acts as an incredibly powerful tool for modern astronomical research. By studying the shape, brightness, and structure of lensed images, researchers can map the distribution of mass in the galactic center with extreme precision, including the detection of dark matter or unseen stellar remnants. The lens acts as a natural, cosmic magnifying glass, magnifying the light of incredibly distant galaxies that would otherwise be far too faint and small for our instruments to detect. It allows observations to peer into the deep, early universe, using the gravity of Sagittarius A as a gravitational booster to reveal baby galaxies that formed in the first epochs of cosmic time. These studies have confirmed Einstein's theory of general relativity with high confidence, showing that even under extreme conditions, the equations remain accurate. The degree of light bending also provides a direct, rigorous test of Albert Einstein's field equations in the strong field regime, showing that the laws of general relativity hold true even in the immediate, extreme vicinity of a supermassive black hole, where gravity is at its strongest, validating our mathematical descriptions of the cosmos. Even closer to the black hole, beyond the region of simple lensing and distortion, lies a critical physical boundary known as the photon sphere. This is a narrow, spherical region located at exactly 1.5 times the Schwarzschild radius of the event horizon, where gravity is so intense that photons, the particles of light, are forced into circular orbits. In this narrow band of space, a photon can orbit the black hole multiple times, circling the dark sphere like a satellite, before either escaping into space due to a slight perturbation or falling inward across the event horizon to be lost forever. Photons that enter this region are on a knife edge, balanced between escape and destruction, a delicate equilibrium that is constantly shifting. Because these orbits are highly unstable, any small disturbance will scatter the light, meaning the photon sphere is a dynamic, transient zone. If a physical observer were somehow able to survive and stand within this photon sphere, directing a beam of light forward, the light from the back of their own head would orbit the black hole and return to their eyes, creating a repeating, infinite loop of self-vision in the dark. The photon sphere is a silent, ghostly shell of trapped, swirling starlight, a place where the distinction between light and matter begins to dissolve under the crushing weight of gravity, holding the light in a perpetual orbital embrace. As the warped light of the galactic center is observed and analyzed, there is a deep realization that what is seen from the safety of Earth is merely a projection, a cosmic illusion shaped by the geometry of gravity. The straightest, most natural path through the universe is sometimes a steep curve, and the stars we map in the night sky are not always where they appear to be, their positions shifted by the unseen masses that lie between. As observers, we are looking at the past, shaped by the gravity of the present, a warped tapestry of light and shadow that continues to drift through the silent void. This bending and warping of light is a quiet reminder of the fluidity of space and time, where the absolute, silent dark of Sagittarius A is framed by a glowing, distorted ring of background starlight, a beautiful, warped border between the visible universe and the invisible void of the event horizon. The cosmic light, traveled across thousands of light years, is shaped by this central giant, leaving a record of the gravity that rules the heart of our galaxy, shining quietly in the deep, velvet night. This glowing boundary is a reminder of the geometric order of the universe, where light and gravity interact to build a cosmic lens that illuminates the dark and lets the mind wonder at the structure of space. In the month of May of the year 2022, humanity obtained its first direct, historic view of the invisible dark heart of our galaxy. For nearly a century, Sagittarius A had been measured, calculated, and inferred through its gravitational effects on nearby S-stars and gas clouds. Yet its physical appearance remained hidden behind dense, dusty lanes of interstellar gas and the absolute, warping veil of its own gravity. The historic image released by the Global Event Horizon Telescope collaboration was a monumental achievement, presenting a dark, central shadow surrounded by a bright, asymmetrical ring of orange-gold light. This light is not the black hole itself, but the glow of superheated gas and plasma orbiting the event horizon at nearly the speed of light, frictionally heated to billions of degrees as it spirals toward the point of no return. The orange-gold colors in the image, although artificially selected to represent the intensity of radio emissions, remind us of a warm autumn leaf drifting in the dark, a visual representation of intense radiation. The image represents a portrait of a boundary, the edge where space-time becomes so warped that not even light can escape. Captured after decades of patient scientific preparation, global cooperation, and mathematical ingenuity, allowing us to see the shadow of the giant. To capture this elusive cosmic shadow, astronomers had to construct a virtual telescope that was effectively as large as the planet Earth itself. The Event Horizon Telescope is not a single, giant instrument, but a global network of radio observatories located in remote, high-altitude sites from Hawaii and the high deserts of Chile to the mountains of Europe and the frozen expanse of the South Pole. Using a technique known as very long baseline interferometry, these widely separated dishes, including the powerful arrays of ALMA and APEX in Chile, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell telescope in Hawaii, and the South Pole telescope, observed Sagittarius A simultaneously in the sub-millimeter band. By synchronization of these signals using hydrogen maser atomic clocks that lose only 1 second every 10 million years, the observatories acted in unison, creating a virtual Earth-sized telescope with an angular resolution capable of reading a newspaper in New York from a sidewalk in London, or seeing a small object on the surface of the moon. These telescopes had to be coordinated down to the picosecond, using atomic clocks to align the radio wavefronts. By using this network, the EHT achieved a resolution equivalent to standing in New York and identifying a golf ball in Munich. This planetary network was absolutely essential, for the black hole appears incredibly tiny in our sky, obscured by the vast distances of the galactic plane, requiring the highest resolution ever achieved. The task of imaging the Milky Way's central supermassive black hole was far more challenging than that of the much larger black hole at the center of the galaxy, Messier 87, which was imaged in 2019. While the latter is a giant of 6.5 billion solar masses that remains stable over days, the material surrounding Sagittarius A, which has a mass of only 4 million suns, orbits the black hole in a matter of minutes, ranging from 4 to 30 minutes. From the perspective of telescopes on Earth, the brightness and structure of the gas ring shifted rapidly during the observations, much like trying to capture a clear photograph of a moving target under low-light conditions, where the target changes shape before the camera can finish its exposure. The plasma is constantly swirling, creating hotspots that orbit the black hole. This makes Sagittarius A a moving target, requiring the creation of specialized software that can reconstruct a movie of the black hole, rather than just a single static frame. Astronomers had to develop new, complex mathematical algorithms to account for this rapid variability, reconstructing the static shadow from a sea of constantly changing data. The final image represents an average of thousands of different reconstructions, a quiet, stable representation of a highly dynamic and chaotic environment, preserving the core structure of the event horizon. The scientific analysis of this image has provided a direct, historic confirmation of Albert Einstein's general theory of relativity under the most extreme gravity conditions. The size of the shadow matches the predictions of general relativity, with an accuracy of within 10%, leaving no doubt that the object at the center of the Milky Way is indeed a supermassive black hole, as described by Einstein's field equations. The asymmetry of the orange ring, with one side appearing slightly brighter than the other, is the result of relativistic Doppler beaming, where the gas and plasma moving toward Earth appears brighter due to its high velocity, while the gas moving away appears dimmer, creating 3 bright spots in the ring. The presence of these magnetic fields is particularly important because they help to explain how black holes launch jets of plasma across light years, showing that magnetic fields are active players in accretion physics. The structure of the ring also revealed the presence of strong, organized, and spiral magnetic fields threading through the superheated plasma, directing the flow of matter toward the event horizon. This confirmation is a triumph of human reason, showing that equations written on a blackboard over a century ago accurately describe the behavior of space-time at the center of our galaxy, confirming the geometry of the void. The processing of the raw observations required a massive computational effort, taking several years of analysis by multiple independent teams before the final image could be released to the public. Because the volume of data was too large, measuring in petabytes, to be transmitted over the internet, the physical helium-filled hard drives from the South Pole Telescope had to wait until the Antarctic spring for planes to fly in before being shipped to supercomputing centers in Germany and the United States. In these specialized facilities, teams of researchers worked in quiet, intense collaboration, using advanced algorithms to calibrate the radio signals, eliminate atmospheric noise, and combine the observations from the different telescopes, double-checking their results through different independent pipelines to avoid any bias. The hard drives, weighing several tons in total, were flown across continents, representing a physical migration of data that mirrors the movements of the stars themselves. This effort highlights the dedication of the researchers involved. This quiet, collective labor of hundreds of scientists around the world was the true engine behind the image, showing that the exploration of the cosmos is a shared human journey, uniting nations and disciplines in a common search for truth. As this historic image is contemplated, it is a reminder of the power of human curiosity to reach across light years of space, to visualize the unseen and understand the invisible. The dark shadow at the center of the ring is the event horizon, a boundary between the known universe and the absolute, eternal unknown, a place where physics as we understand it reaches its absolute limit. The golden ring of light that surrounds this shadow is like a campfire in the cosmic night, illuminating the edge of the void and drawing the mind into the deep mysteries of space and time, inviting contemplation. It is a symbol of our capacity to see in the dark, using the light of stars and the power of collective intellect to map the shadows of the cosmos, showing that even the most massive giants cannot remain completely hidden from our view. It suggests that though we are small, our minds can grasp the structures of the universe, bridging the gap between our brief lives and the eternal cycles of the stars. Resting in the peace of this realization, the image is a quiet, beautiful testament to our connection with the stars, shining quietly in the deep, velvet night. In the study of the cosmos, astronomers often seek out the most luminous, active, and dramatic objects, such as distant quasars that outshine entire host galaxies from the edge of the visible universe, or active galactic nuclei that launch powerful jets of plasma across light years of space. Yet, when attention is turned to Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy, a very different and far more peaceful reality is encountered. Despite possessing over 4 million times the mass of the Sun, Sagittarius A is remarkably quiet, existing in a state of near-complete dormancy and silence. It does not shine with the blinding light of active systems, nor does it consume stars with a voracious, destructive hunger that would disrupt the surrounding space. Instead, it sits in the absolute dark, like a sleeping giant, barely sipping on the thin gas and stellar winds that drift nearby. This quietness is a profound mystery, representing a state of extreme starvation in a region that is otherwise crowded with massive stars, dense gas clouds, and intense gravitational energy. For decades, researchers have puzzled over why this massive point of gravity is so inactive compared to the giants in neighboring galaxies, such as the supermassive black hole at the center of Messier 87, which glows with the brightness of billions of suns and launches a jet of plasma that extends far beyond the galaxy itself. Sagittarius A, in contrast, remains a silent and mysterious anchor, holding the Milky Way together without the violent fireworks seen in other cores, creating a peaceful harbor of gravity in the deep void. The galactic center is not lacking in material. It is filled with dense molecular clouds, powerful stellar winds from massive stars, and passing suns that should provide a constant, rich feast for the central black hole's gravity. This creates a striking and beautiful paradox that challenges simple models of black hole accretion. There is an abundance of fuel, yet the black hole remains inactive and starved, barely consuming enough matter to sustain a faint glow. The explanation for this starvation lies in the complex thermodynamics of the gas surrounding the event horizon, described by the radiatively inefficient accretion flow, or RIAF model. As gas falls toward the black hole, it is compressed and heated by gravitational forces. However, because the density of the gas in the inner accretion flow is relatively low, the individual particles rarely collide, meaning they cannot transfer energy to electrons and cool by emitting radiation. The material remains extremely hot, with temperatures reaching billions of degrees. At these extreme temperatures, the individual gas particles move with rapid, random thermal motion, giving them too much kinetic energy to fall smoothly into the gravitational well. Instead of spiraling inward across the event horizon, the hot gas expands, and much of it is blown away by its own thermal pressure before it ever reaches the point of no return, leaving the black hole starved and surrounded by a hot, diffuse envelope of escaping gas. In addition to this thermal barrier, the region surrounding Sagittarius A is threaded with powerful, organized magnetic fields that act as barriers to accretion. These fields act as physical guides, shaping the flow of the hot plasma and preventing it from accreting smoothly. The magnetic lines of force twist and bundle together, forcing the gas into specific, structured paths that channel it away from the black hole, rather than allowing it to fall directly inward. It is a process of magnetic regulation, where the magnetic pressure resists the pull of gravity, keeping the material at bay. This state is known to astrophysicists as a magnetically arrested disk, or MAD state. Observations suggest that less than 1/10,000,000th of a solar mass is consumed by Sagittarius A per year, which is equivalent to eating a few crumbs of bread on a planetary scale. Less than 1% of the gas that enters the outer accretion disk actually makes its way across the event horizon. The remaining 99% of the material is expelled in giant, diffuse outflows, carried back into the crowded stellar cluster, a process of cosmic recycling that prevents the black hole from growing rapidly and maintains the quiet balance of the core, showing that magnetic fields are active players in regulating the growth of the central giant. If this accretion process were even slightly more efficient, the galactic center would be a very different, far more hostile place. A higher feeding rate would transform the core into a blinding source of X-rays and gamma radiation, bathing the entire galaxy in high-energy light that would sterilize surrounding space and strip the atmosphere of any developing world. Such intense radiation would strip the protective atmospheres of planets in nearby systems and disrupt the molecular clouds necessary to form new stars, changing the evolutionary path of the Milky Way. The inefficiency of Sagittarius A's feeding is therefore a shield, protecting the wider galaxy from the destructive potential of its central giant. The silence of the core is a necessary condition for the stability of the spiral arms, allowing stars like our Sun to exist in a calm, protected environment where planets can form and life can develop. This galactic habitable zone exists because the central giant is quiet, functioning as a silent protector of our stellar neighborhood, ensuring that the quiet dance of life can proceed undisturbed in the outer disk, far removed from the high-energy events that dominate the centers of active galaxies. This dormancy, however, is not absolute. While the supermassive black hole is quiet, it is not completely inactive or dead. Space observatories, including Chandra, Swift, NuSTAR, and the JWST, have detected brief, sudden flares of X-ray and infrared radiation coming from the immediate vicinity of the event horizon. These flares, lasting from minutes to hours, represent small clumps of gas, or perhaps even stray comets or asteroids that have drifted too close and been shredded by tidal forces before being consumed, heating up dramatically just before they disappear. These transient events are like the quiet whispers of a sleeping giant, brief moments of activity in an otherwise peaceful slumber. They provide astronomers with fleeting glimpses into the physics of the accretion region, showing that even in its quietest state, the black hole remains a dynamic entity. These brief flashes of light, occurring several times a day, illuminate the inner light hours of the galactic center, showing that the giant still stirs, consuming the debris of its environment in small, silent bites and reminding us of the ongoing interaction between gravity and matter. The quietness of Sagittarius A offers a profound shift in perspective. In a universe that is often described through terms of violence, collision, and consumption, the most massive object in our galaxy exists in a state of quiet balance and peace. The silence at the heart of the Milky Way is not a sign of inactivity or decay, but rather a delicate equilibrium of thermal and magnetic forces that keeps the central giant at rest. It is a reminder that the most powerful entities in the cosmos do not need to display their strength through constant noise, radiation, and destruction. Instead, they can exist as quiet anchors, holding the galaxy together in a calm, silent dance that has continued for billions of years. As we contemplate this sleeping giant, we feel the calm and order that underlies the galactic center, a quiet harbor of gravity in the deep void, showing that even the most extreme points of density can exist in a state of peaceful repose, guiding the galaxy with a silent hand, and allowing the stars to complete their orbits in peace and quietness. In the quiet expanse of the galactic core, a force is at work that warps not only the arrangement of matter but the very structure of space and time itself in a way that is difficult to comprehend. A supermassive black hole is defined not only by its immense mass and its event horizon, but also by its spin, which represents the rotation of the central singularity. In the years 2024 and 2025, observations from the Event Horizon Telescope focused on the polarization of light surrounding Sagittarius A. These measurements map the orientation of magnetic fields threading through the accretion region, revealing that the black hole is not a stationary sinkhole, but is spinning with speed. The data indicates that Sagittarius A possesses a spin parameter of above 0.9, meaning it is rotating at more than 90% of the maximum rate allowed by the laws of physics. At this rate, the boundary of the event horizon is moving at velocities that approach the speed of light, twisting the surrounding universe into a spiral and dragging space-time along with its spin. This discovery has changed our understanding of black hole physics, showing that Sagittarius A is a reservoir of rotational energy, storing the momentum of all the matter that has fallen into it over the course of galactic history. This rapid rotation creates an effect known as frame dragging, or the Lentz-Thirring effect, where the spin of the black hole drags the very fabric of space-time around with it. Space-time is not an empty, passive stage, but a flexible, dynamic medium that can be bent, stretched, and twisted by the presence of mass and motion, much like a thick, viscous fluid. Near the event horizon, the warping of space-time is so severe that a region is created called the Ergosphere, an oblate spheroidal space that envelops the black hole. Within this space, the twisting of space-time is so absolute that it is physically impossible for any object to remain stationary relative to the distant stars, regardless of how much energy is expended or how powerful its propulsion might be. Regardless of how much energy is expended, any particle, star, or beam of light is forced to rotate in the direction of the black hole's spin, swept along by the current of space. Space-time itself is in motion, carrying everything nearby along in a silent, cosmic whirlpool that circles the dark center. This region is bounded on the outside by the static limit, where the force of rotation first begins to dominate, and on the inside by the event horizon itself, forming a pressurized shell where energy can be extracted from the black hole's spin through processes like the Penrose mechanism, converting rotation into raw energy, showing that the black hole is a massive gravitational engine. The measurement of this high spin parameter provides astronomers with a valuable window into the evolutionary history of Sagittarius A. A supermassive black hole can only increase its rotation rate by accreting matter that carries angular momentum or through mergers with other black holes. If the history of the galactic core had been dominated by chaotic, random events such as gas clouds, falling inward from different directions, or mergers with smaller black holes on random orbits, the opposing rotational motions would have canceled each other out, leaving the central black hole with a low spin. The discovery of a spin parameter above 0.9 indicates a long, peaceful history of orderly feeding. For billions of years, gas must have spiraled into the event horizon from a single, consistent direction, gradually spinning up the black hole much like a gentle, repeat push accelerates a spinning top. This spin is a record of the ancient history of our galaxy, preserved in the twisting of space itself, showing that the central regions of the Milky Way have enjoyed a long period of stability and order that allowed this spin to build up. This indicates that the core was not subjected to major, disruptive galactic mergers for the last several billion years, allowing the accretion disk to remain stable and feed the black hole in a highly aligned and consistent manner, quiet and undisturbed. This high rotation rate also has a profound effect on the immediate surroundings of the black hole, shaping the structure of the inner accretion flow. In physics, a spinning mass pulls the innermost stable circular orbit closer to its event horizon. For Sagittarius A, this means that the gas in the accretion disk can orbit much closer to the point of no return than it would around a non-spinning black hole. This close proximity increases the gravitational heating of the gas, creating a brighter, more compact ring of emission that glows across the radio spectrum. The spin also facilitates the extraction of rotational energy from the black hole itself. Magnetic field lines, twisted by the rotation of the ergosphere, can channel this energy outward, creating powerful winds that push against the surrounding gas and influence the wider environment of the galactic center. This coupling between spin and magnetic fields is key to understanding how the black hole interacts with its host galaxy, regulating the flow of matter and energy in the core, directing the pathways of the plasma, and preventing the system from collapsing into complete chaos, maintaining a structured accretion disk that flows in perfect harmony with the central rotation, a giant engine operating in the quiet of space. The study of this rotation is a triumph of modern observational astronomy, relying on the detection of polarized light. Polarization refers to the orientation of light waves as they travel through space. When light passes through the strong magnetic fields of the accretion disk, its polarization pattern is altered, carrying information about the direction and strength of those fields back to Earth. By analyzing these subtle signals, researchers have been able to reconstruct the magnetic structures that thread through the ergosphere, demonstrating that they are organized and strong enough to influence the accretion process. This polarization data has provided the key to unlocking the spin of the black hole, turning a theoretical prediction of relativity into an observed reality. The radio waves, captured by the planetary array of telescopes, are processed over months to isolate these polarized alignments, creating a magnetic map of the innermost boundary of our galaxy, revealing the lines of force that guide the hot plasma, showing the structure of the magnetic fields, and demonstrating that gravity and electromagnetism are bound together in a single, elegant system that governs the heart of the galaxy. This detailed mapping allows astronomers to trace the paths of magnetic lines as they spiral into the event horizon, showing how they resist the pull of gravity and regulate the accretion flow, a level of detail that was once considered science fiction. As the rotation of Sagittarius A is contemplated, there is a realization that space-time possesses a form of memory, preserving the history of all the matter that has fallen into the core. The rapid spin observed today is the physical consequence of millions of tons of gas falling into the core in an orderly fashion over billions of years. It is a record of the ancient history of our galaxy, preserved in the twisting of space itself. The silent, rapid rotation of the central giant continues to shape the motion of the stars and the gas, a twisting vortex in the dark that connects the origin of the Milky Way to its present state, spinning quietly in the absolute stillness of the cosmic night, guiding the stars in their orbits, reminding us of the orderly patterns that govern the universe, and leaving a trace of past movements in the geometry of empty space. In the grand scale of the universe, this rotation is a quiet reminder of the persistence of motion, where the central anchor of our galaxy spins silently and perpetually, a cosmic flywheel that will continue to spin long after the last stars have faded into darkness, a monument to the laws of motion that govern all things, holding the stellar metropolis in a stable, rotating balance that proceeds with a calm regularity, a quiet lighthouse of gravity in the deep, velvet night. Surrounding the event horizon of Sagittarius A lies a structure of light and energy that represents one of the most energetic environments in the cosmos. Yet from our distance of 26,000 light-years, it appears as a soft, flickering glow in the dark. This is the accretion disk, a thick, three-dimensional ring of superheated gas and plasma that spirals toward the point of no return. Unlike the flat, frozen rings of ice and dust observed around the planet Saturn, this disk is a dynamic, churning fluid, heated by friction and gravity to temperatures of millions of degrees. At these scales, the atoms are stripped of their electrons, creating a plasma that glows across multiple wavelengths of light, from the low-frequency radio waves that can pierce the galactic dust to the high-energy X-rays that record the most events close to the horizon. The disk is not uniform, but is composed of layers of gas, orbiting at different velocities, with the inner regions moving at significant fractions of the speed of light, creating a vortex of heat and radiation in the dark, shining in the void, and forming the glowing ring of starlight that marks the border of the event horizon. This ring is a beacon of light, carrying the energy of gravity out into the surrounding space. This radiation travels across the cosmos for 26,000 years, carrying vital information about the physical environment near the event horizon directly to our telescopes, helping us decode the secrets of the core. The physics of this disk is shaped by the rapid rotation of the central black hole. As Sagittarius A spins, its high spin parameter drags the surrounding spacetime, creating a frame-dragging effect that influences the orientation of the innermost material. This force does not simply pull the gas inward. it forces the plane of the inner accretion disk to wobble. This motion, known as lens-thurring precession, is similar to the behavior of a toy spinning top as it begins to slow down, its axis tracing out a slow, circular cone in space. Because Sagittarius A is relatively compact for a supermassive black hole, this precession occurs on timescales of only minutes to hours. The inner edge of the disk is in a state of constant, rhythmic wobbling, tilting its plane relative to the outer regions of the disk and the line of sight from Earth, creating a dynamic, shifting geometry that wobbles like a flower petal in a cosmic wind, continuously changing the orientation of the accretion disk and creating a wave that travels through the plasma, a rhythmic ripple in the river of fire that circles the event horizon. This wobble is a direct consequence of the frame dragging effect, where the spin of the black hole forces the gas to align with its spin axis, creating a complex, twisted structure where the inner and outer parts of the disk are tilted at different angles, a beautiful, fluid spiral. This precession creates a flickering effect in the radiation observed from the galactic center. As the inner disk tilts, different portions of the superheated plasma are brought into view, and the light is shifted by relativistic effects. When the gas tilts toward Earth, its emission is amplified by Doppler boosting, appearing brighter to telescopes. When it tilts away, its light dims. This constant, rhythmic precession causes the observed radio and infrared emission to vary rapidly over short intervals, presenting a challenge for astronomers attempting to capture a stable image of the event horizon. It is like attempting to photograph an object through a shifting mirror, where the reflection is constantly bending and moving in response to the invisible rotation of the black hole, requiring advanced algorithms to decode and reconstruct the structure of the inner flow, showing how light is bent, and producing a repeating pattern of light and shadow. The light we record is therefore a modulated signal, carrying the frequency of the precession in its brightness, a cosmic heartbeat that tells us of the black hole's rotation ticking away in the absolute silence of the galactic core. By analyzing these fluctuations, researchers can determine the period of the precession, which in turn tells us about the spin and mass of the black hole, a key data point in our exploration. The structure of the disk is further complicated by the powerful magnetic fields that thread through the plasma. These fields are not passive, they actively shape the flow of matter. Because the inner parts of the disk orbit much faster than the outer regions, the magnetic field lines become twisted and tangled, building up tension like a tightly wound spring. When the tension becomes too great, the field lines snap and reconnect in a process called magnetic reconnection. This event releases energy, heating localized pockets of gas, and producing sudden flares of light. These magnetic processes, working in harmony with the lens-thurring precession, create a complex, three-dimensional environment where gravity, rotation, and electromagnetism are all bound together. The twisted magnetic fields can also channel some of the plasma away from the disk entirely, flinging it outward in faint, high-speed winds that represent the quiet whispers of the black hole's energy escaping, carrying angular momentum away and shaping the environment of the central light years, acting as a relief valve for the intense pressures. This magnetic turbulence is a key source of viscosity, allowing the gas to lose its orbital energy and spiral inward, a crucial step in the accretion process that feeds the black hole. This wobbling of the accretion disk remains a hidden aspect of the galactic center, undetected by traditional imaging methods. Astronomers must rely on the analysis of polarization and variability to infer its presence. By monitoring the changes in the polarization angle of the radio waves over hours, researchers can trace the movement of the hotspots within the disk, mapping the circular path of the precession. This work has shown that the inner accretion disk is not a static ring of gas, but is a fluid system, responsive to the warping of space-time. It is a level of detail that was once considered impossible to measure, revealing the motions of matter just outside the border of the event horizon, giving a voice to the invisible and allowing astronomers to test general relativity in real time, proving the theories of space-time warping with high precision, and showing that even the most massive anchors are fluid. This fluid precession shows that gravity is not just an attractive force, but is a geometric guide that shapes the motions of matter in complex and beautiful ways, transforming the accretion disk into a three-dimensional wave that dances around the black hole, a silent and elegant ballet of light and space. The precession of the accretion disk provides a reminder of the fluid nature of the cosmos. Around the most massive and solid gravitational anchor in our galaxy, there is no static ground, only a flowing river of plasma that bends and wobbles in response to the twisting of space and time. The hot gas moves in a repeating pattern of motion, a wave that circles the event horizon in the dark. As this cosmic top spins, it creates a rhythm of light and shadow, a quiet, shifting dance of energy that continues to unfold at the very edge of the invisible void, whispering its secrets across the empty reaches of the galaxy, a silent beacon of light that guides the mind into the quiet order of the cosmos, spinning quietly in the absolute stillness of the infinite night. This motion is a quiet comfort, showing that even in the most extreme environments, there is a repeating, predictable order, a steady pulse that connects the smallest particles of dust to the grand movements of the galaxy, resting in the stillness. We are observers of this silent wave, watching it circle the edge of the unknown, a beautiful and orderly pattern of light that continues to shine in the deep, velvet dark, holding the galaxy together in a calm, eternal dance. In the quiet depths of the galactic center, where the sleeping giant Sagittarius A rests, the silence is not entirely unbroken. While the black hole remains dormant and quiet for the majority of the time, its long slumber is periodically interrupted by sudden, bright events known as flares. These are brief, localized bursts of X-ray and infrared radiation that originate from the very edge of the event horizon, lasting only a few hours. To an observer with instruments sensitive to these frequencies, the calm, dark accretion disk would suddenly display a brilliant pinpoint of light, glowing with intense radiance, before fading back into the background noise over the course of a few hours. These flares represent the quiet giant's brief moments of activity, small gasps of light that reveal the ongoing interaction between the black hole and the matter that wanders too close to its boundary. These events show that the core is not a completely static void, but is reactive, responding to the arrival of new material with sudden, bright releases of energy that temporarily light up the dark. This magnetic reconnection and plasma heating represents a direct connection between the black hole and its environment, showing that the dormancy of the core is not a state of complete stasis, but a balance between gravity and thermal pressure. The flares erupt unpredictably, like sparks flying from a dying fire, revealing the hidden dynamics that continue to operate in the absolute darkness of the galactic center, where gravity coordinates the movements of all matter. The physical cause of these sudden flares lies in the consumption of small, stray objects that enter the gravitational influence of the central mass. The space surrounding Sagittarius A is not empty, but is filled with a thin distribution of gas, dust, and planetary debris, including comets and asteroids that have been flung from their home star systems by close stellar encounters. When one of these small bodies wanders into the inner light hours of the galactic core, it is captured by the immense gravity of the giant. As the asteroid or comet spirals closer to the event horizon, the tidal forces stretching it become immense, shredding the solid body or gas cloud into a long, thin stream of material in a process of gravitational disruption. As this stream collides with the hot plasma of the accretion disk, friction heats it to billions of degrees, releasing a burst of energy in the form of X-rays and infrared light just before the matter is consumed by the black hole. This process, similar to meteors burning up in Earth's atmosphere, releases energy equivalent to millions of thermonuclear explosions, a final flare of light before the object crosses the event horizon. This intense release of energy provides a fleeting beacon of light that astronomers can detect across the vast dust lanes of the Milky Way, mapping the final moments of matter as it is pulled into the gravitational void, converting solid structures into pure radiation. During these flares, astronomers have detected a phenomenon known as quasi-periodic oscillations. These are regular, repeating pulses in the brightness of the flare, occurring on timescales of only a few minutes. This periodic pulsing is not random. It represents the orbital motion of superheated hotspots of gas circling the black hole at significant fractions of the speed of light near the innermost stable circular orbit allowed by the laws of physics. As a hotspot of plasma orbits within the warped spacetime near the event horizon, its light is periodically focused and boosted by the gravity of the black hole, creating a strobe-like effect that is recorded by detectors on Earth. These oscillations are the heartbeat of the flare, providing a direct measurement of the orbital speeds of matter at the absolute limit of physical stability, where space and time are warped. The gravity instrument on the VLT has tracked these hotspots in real time, showing them orbiting at 30% of the speed of light, providing a direct confirmation of the geometry of the innermost orbit allowed by physics. This detailed observation allows researchers to test general relativity in its strongest regime, showing that the warp of spacetime behaves exactly as predicted by Einstein's field equations, with hot plasma tracing out circular paths at the edge of the void. The detection of these flares requires the cooperation of multiple space-based and ground-based observatories. Instruments like the Chandra X-ray Observatory, the NuSTAR telescope, and the JWST are used to monitor the galactic center, recording the changes in brightness over days. The data collected presents a quiet baseline representing the dormant state of the black hole, which is suddenly interrupted by a sharp spike in energy, followed by a slow, gradual decay. By comparing these observations across different wavelengths, astronomers can calculate the temperature, density, and size of the emitting region, mapping the physical conditions of the gas just outside the event horizon. These flares are relatively rare, occurring only once or twice a day, making each event a valuable opportunity to study the behavior of gravity in its most extreme form. By observing how the flares change in color and intensity, researchers can build detailed computer simulations of the accretion flow, tracing the paths of the gas as it is pulled into the event horizon. This global coordination allows us to construct a three-dimensional model of the accretion region, turning the faint radio whispers of the core into a detailed map of the physical processes that govern the boundary of the supermassive black hole. The study of these flares has revealed a hidden aspect of the black hole's environment. The frequency of the quasi-periodic oscillations is directly related to the spin of the black hole and the structure of the surrounding spacetime. By measuring these pulses, scientists can test different models of general relativity, confirming that the geometry of space close to Sagittarius A matches the predictions of Einstein's equations. The flares also show that the quietness of the black hole is a dynamic state, constantly responding to the arrival of new material. It is a reminder that even in its dormancy, the black hole remains an active participant in the physics of the galactic core, its gravity continuing to draw in and consume the dust and debris of the surrounding space. This magnetic reconnection and accretion energy represents a connection between the black hole and its environment, showing that the dormancy of the core is not a state of stasis, but a balance between the forces of gravity and pressure. The magnetic field lines, twisted by the rotation of the accretion disk, periodically snap and rearrange, releasing energy that heats the gas and creates the hotspots that we observe as pulsating flares, demonstrating the deep connection between gravity, rotation, and electromagnetism. As these brief flares of light are contemplated, they offer a reminder of the transient nature of activity in the cosmos. The bright flashes that illuminate the edge of the event horizon are temporary, lasting only a short time before the gas is consumed and the light is extinguished forever. The black hole returns to its quiet, dark state, the silence of the core restoring itself as the giant slips back into its long slumber. It is a beautiful, repeating cycle of light and shadow, where the quiet of the galaxy is briefly broken by the whisper of falling matter, a final song of energy sung at the very border of the invisible void before entering the absolute quiet of the black hole. The stars continue to orbit in the dark, the core returns to its quiet rest, and the silence of the galactic night remains undisturbed, a testament to the order and balance that governs the center of our galaxy, shining quietly in the deep void. This rhythmic breathing of the core is a comfort, showing that the most extreme processes in the universe are temporary, eventually fading back into the peaceful silence that has ruled the galactic center for billions of years, and will continue to rule for eons to come. In the crowded fields that surround the central void, a population of stars exists that challenges our most basic understanding of how suns are born and grow. As telescopes zoom out from the event horizon of Sagittarius A, they reveal a cluster of incredibly bright, massive stars that burn with a hot, blue-white radiance. These are O-type and Wolf-Rayet stars, among the most luminous and energetic suns in the known universe, some weighing more than 100 times the mass of our Sun. Because they burn their nuclear fuel so rapidly, their lifespans are short, lasting only a few million years before they exhaust their hydrogen and collapse. In the timescale of the galaxy, these stars are young infants, having formed only yesterday. Yet, their presence in this immediate vicinity of the supermassive black hole is a profound mystery, representing a stellar paradox that astronomers refer to as the paradox of youth, which has puzzled researchers for decades because it challenges the standard theories of star formation. The immense gravity of the central giant should prevent the cold molecular gas clouds from collapsing to build stars, yet here they shine, bright and young in the dark core. These young giants pour out torrents of ultraviolet radiation and powerful stellar winds, illuminating the surrounding gas clouds and creating glowing nebulae that drift through the crowded space like cosmic clouds of purple and magenta. These massive stellar engines burn with a blinding, hot intensity, casting their bright light across the dusty lanes of the nuclear star cluster, creating a complex web of ionized gas. To understand why these young giants represent a contradiction, it is necessary to examine how stars normally form in the cosmos. The birth of a sun requires a vast, cold cloud of hydrogen gas and dust to slowly collapse under the pull of its own gravity over millions of years, drawing tighter and hotter until nuclear fusion ignites at its core. But near Sagittarius A, the gravitational forces are not uniform. They are marked by intense tidal gradients. The gravitational pull on the near side of a gas cloud is far stronger than on the far side, creating a stretching force that tends to pull the cloud apart. In this region, any gas cloud attempting to collapse into a star should be shredded by the black hole's tidal forces long before it can reach the densities required for fusion. The center of the galaxy should be a stellar desert, completely empty of young stars, yet these blue giants orbit there in abundance, defying the tidal forces of the central giant and forcing scientists to search for alternative models of star birth that can operate in high-gravity environments, where the standard laws of collapse are challenged. The existence of these massive stars suggests that there are pathways to star formation that we are only beginning to understand, where extreme density can overcome the disruptive effects of tidal shear. The intense tidal forces of the central giant pull at the molecular clouds, stretching and shearing the gas before it can collapse under self-gravity, testing the absolute limits of stellar physics. One prominent theory proposed to resolve this mystery suggests that the stars formed within a dense, massive disk of gas that once surrounded the black hole. Several million years ago, a massive cloud of gas must have been captured by Sagittarius A, forming a rapid, rotating disk of plasma and dust. Within this disk, the gas density was so high that the self-gravity of the material was strong enough to resist the tidal forces of the black hole, allowing the gas to collapse. This allowed the disk to fragment into thousands of smaller clumps, which collapsed to form a generation of massive stars in a single, rapid burst of birth, creating a coplanar stellar population. Once the stars were formed, the remaining gas was dispersed by stellar winds and the radiation of the new suns, leaving behind the stellar cluster observed today, orbiting in a relatively flat plane around the central mass, a record of a forgotten era of intense gas capture and star formation. This disk formation theory explains the highly aligned orbits of these young giants, showing that they were not captured individually, but were born together in a single, massive disk of gas that once spiraled around the black hole, transforming the core into a starburst nursery. This disk fragmentation mechanism represents a unique pathway for starbirth in extreme environments, showing that gas can collapse even under tidal shear, creating a family of sister stars. An alternative hypothesis suggests that these young travelers did not form near the black hole at all, but were born farther out in the galaxy, where the environment is quiet and star formation can proceed normally. In this scenario, the stars must have migrated inward to their current positions. This migration could have been driven by gravitational interactions within a dense star cluster, where close encounters between stars slowly shifted their orbits closer to the center. This process, known as dynamical relaxation, requires a dense stellar cluster to operate, gradually sinking the most massive members toward the core. Some researchers have also suggested that the migration was aided by the presence of a second, intermediate mass black hole that once orbited Sagittarius A. This unseen companion would have acted as a gravitational tugboat, pulling the young stars inward before eventually being consumed by the central giant, leaving the stars behind in their current, close orbits. This dynamical pathway highlights the complex history of the core, showing that the stars we observe today may have traveled thousands of light-years to reach their current, hyperspeed trajectories. This inward drift represents a long and complex dynamical journey, where the orbital energy of the stars is slowly transferred to the surrounding stellar field, leading to a crowded core. Regardless of the precise mechanism, the presence of these young giants indicates that the history of the galactic center is marked by periods of activity and change. The core is not a static environment where nothing new can form, but has experienced cycles of intense star formation, driven by the arrival of gas clouds from the outer galaxy. The massive blue stars burn bright and live short lives, destined to explode as supernovae in a few million years, leaving behind stellar mass black holes and neutron stars that will join the silent swarm orbiting the core. This cycle of birth, life, and death continues to unfold at the very heart of the Milky Way, driven by the gravitational engine of Sagittarius A. The energy released by these stars shapes the surrounding gas, blowing away the dust and creating channels of empty space through which light can travel, regulating the accretion flow and shaping the long-term evolution of the galactic core. Each supernova explosion enriches the central environment with heavy elements, providing the raw materials for future generations of stars. The winds from these O-type stars blow away the surrounding dust, creating a complex structure of cavities and shells in the nuclear star cluster, which shapes the paths of incoming gas clouds. These young cosmic travelers are a quiet testament to the capacity of the universe to create structure in the most hostile environments. At the edge of the void, where tidal forces seek to rip gas clouds apart, these massive suns continue to burn, casting their blue light across the dark. They are a reminder that the forces of creation and growth are fundamental to the cosmos, finding ways to succeed even under the pressure of the galaxy's most massive gravity. They orbit in perfect, silent circles around the dark center, their light illuminating the edge of the unknown, a brilliant testament to the persistence of light in the deep dark of space, showing that star formation can adapt to even the most extreme gravitational conditions, spinning quietly in the absolute stillness of the galactic night. As we watch these young giants glide through the vacuum, we are reminded that the universe is a place of perpetual renewal, where the light of new suns is born at the very border of the absolute dark, tracing out their orbits in perfect harmony. They proceed in their silent orbits, a clockwork system of light and gravity that has lasted for millions of years, tracing out a beautiful rosette pattern in the sky and providing a stable coordinate system for astronomers watching from afar. To understand the existence of Sagittarius A, it is necessary to travel not only inward toward the core but backward through the deep reaches of cosmic time. The universe we observe today is mature, filled with structured galaxies and stable star systems. But billions of years ago, in the first epochs following the Big Bang, the cosmos was a dark, cold expanse, filled only with primordial hydrogen and helium, devoid of the heavier elements that build planets and stars. Inside this ancient mist, the first structures began to condense, and the seeds of the first supermassive black holes were planted. The origin of these central giants represents one of the most significant mysteries in modern astrophysics, presenting a timeline that challenges our understanding of how quickly matter can gather under the influence of gravity. How could these black holes reach masses of millions or billions of suns in such a short amount of time? The early universe was a place of rapid transformation where gravity operated on a grand scale, drawing gas clouds together to build the foundations of the first galaxies, and planting the seeds that would eventually grow into the supermassive anchors we see today. This early period of cosmic history was marked by rapid density changes, where the first structures began to coalesce under gravity, forming a web of dark matter and primordial gas that guided the evolution of the first stellar systems. The growth of a black hole is governed by a fundamental physical balance, known as the Eddington limit. When gas spirals inward toward a gravitational center, it is compressed and heated, releasing energy in the form of radiation. This radiation pressure pushes outward, resisting the inward pull of gravity. The Eddington limit represents the point of equilibrium, where the outward push of light balances the inward pull of mass, establishing a maximum rate at which a black hole can steadily consume matter. If a supermassive black hole like Sagittarius A began its life as a stellar mass seed formed by the collapse of a single normal star, it would have to feed at this maximum limit without interruption for hundreds of millions of years to reach its current mass of 4 million suns. For the even larger black holes discovered in the early universe, this timeline is impossible, as they achieved masses of billions of suns within less than 1 billion years of the Big Bang, indicating that they grew by other means, bypassing the standard limits of accretion, and suggesting that the first generation of seeds were far larger than any black holes formed in the modern universe. This physical limit represents a strict bottleneck for growth, meaning that black holes must have accreted matter at super Eddington rates in short bursts of extreme feeding. This challenge has led astronomers to propose that supermassive black holes did not start as small stellar seeds, but were born large. One leading theory involves the direct collapse of massive gas clouds in the early universe. In this scenario, giant clouds of pristine gas, containing hundreds of thousands of solar masses, collapsed directly under their own gravity without first fragmenting into individual stars. This process, known as direct collapse, would bypass the stellar life cycle entirely, creating a seed black hole that weighed tens of thousands of times the mass of the Sun right from the beginning. These massive seeds would then have a significant head start, allowing them to grow into supermassive black holes more easily through the steady accretion of surrounding gas, accelerating the timeline of growth and explaining their early presence in the history of the cosmos. This direct collapse pathway requires unique conditions, such as a strong background of ultraviolet radiation from nearby stars that prevents the gas cloud from cooling and fragmenting, allowing the entire cloud to collapse as a single, massive entity directly into a gravitational void. This rapid collapse bypasses the normal stellar stages, creating a massive singularity that can immediately begin to accrete surrounding gas and act as the core of a new galaxy. Another hypothesis centers on the existence of hypermassive primordial stars, often referred to as population 3 stars. Because the early universe lacked heavy elements like carbon and iron, gas clouds could not cool as quickly, allowing stars to grow to sizes that are impossible in the modern cosmos. These ancient giants, weighing thousands of times the mass of the Sun, would burn their fuel with speed, living for only a few million years before collapsing directly into massive stellar remnants. These hypermassive seeds would then merge with one another and consume gas, gradually building the foundations of the central black holes that now anchor the galaxies forming the seeds of supermassive black holes like Sagittarius A in a short geological time. This primordial pathway highlights the role of the first stars in shaping the cosmos, showing that the birth of supermassive black holes was intimately connected to the first generation of star formation, where the absence of chemical enrichment allowed for the creation of massive stellar engines that would have been unstable in later epochs of cosmic history. These ancient suns, composed only of pristine hydrogen and helium, were the first light sources in the universe, burning bright in the absolute dark before collapsing. The search for these ancient seeds represents one of the primary missions of modern space observatories, particularly the JWST. By looking across billions of light-years of space, telescopes can observe galaxies as they existed in the first stages of cosmic history, acting as a time machine. These observations allow astronomers to search for the faint, high-energy signatures of growing seed black holes, testing the different theories of direct collapse and primordial star mergers. The data collected has begun to reveal a population of early, massive black holes, showing that the growth of these central anchors was intimately connected to the birth and evolution of the first galaxies, shaping their structures and directing the formation of stars in the early universe. By mapping the correlation between galaxy mass and central black hole mass across cosmic time, researchers can trace the history of this coevolution, showing that the central giants and their host galaxies grew together in a coordinated, gravitational partnership that has lasted from the dawn of time to the modern era, creating the stable systems we observe today. These observations are critical for checking our cosmological models, showing how the first central giants and their galaxies grew in tandem, shaping the core. The story of the first seeds is a reminder of the relationship between the small and the large in the cosmos. The supermassive gravity of Sagittarius A, which now governs the movements of hundreds of billions of stars in our galaxy, began as a simple, quiet seed in the ancient dark of the early universe. It grew slowly, through the accumulation of gas and the mergers of smaller systems over billions of years, transforming from a tiny point of density into the gravitational anchor of the Milky Way. It is a testament to the power of time and gravity to shape the universe, showing that even the most massive structures have simple, humble origins, growing quietly in the dark of space and holding the galaxy together in a calm, eternal dance. As we look at the galactic center today, we are looking at the end result of this long history, a monument to the ordering principles of gravity that has survived for billions of years, tracing its origins back to the first gas clouds that condensed in the silent, early dark of the cosmos. It has grown from a tiny seed in the early universe into the supermassive giant that now anchors our galaxy, proceeding in perfect order and guiding the paths of hundreds of billions of stars in their slow, perpetual dance through the intergalactic void. Looking forward into the deep future of our galaxy, beyond the lifespans of stars and the stability of the solar system, a grand event awaits the Milky Way. Currently, the Andromeda galaxy, our nearest large neighbor, lies 2.5 million light-years away, drifting through the intergalactic void. But this distance is shrinking. Andromeda is approaching our galaxy at a velocity of approximately 110 kilometers per second. Over the next few billion years, an observer on Earth would watch Andromeda grow larger and more prominent in the night sky, transforming from a faint, fuzzy patch of light into a magnificent spiral structure that stretches across the heavens, eventually dominating the night sky and casting a soft, galactic glow over the landscape before the merger begins. In about 4.5 billion years, this motion will culminate in a cosmic collision, a merger of two massive stellar systems that will completely reorganize our neighborhood of space, transforming the two separate galaxies into a single, giant elliptical galaxy that astronomers call Milomeda. This merger will rewrite the geometry of the local group, bringing together hundreds of billions of stars into a single, massive stellar city that will span hundreds of thousands of light-years, establishing a new order in the intergalactic void. This slow approach is guided by the gravitational bonds of the local group, which pulls the two systems together in a silent, inevitable fall. From a human perspective, the word collision suggests a violent and destructive impact, but on the scale of the cosmos, the collision of two galaxies is a slow and silent interpenetration. The distance between individual stars is so vast that physical collisions between suns are extremely rare. Stars will pass by one another like two swarms of bees passing through the same forest, their orbits altered by gravity but their physical structures remaining untouched. However, the gas clouds within the two galaxies will collide and compress, triggering a massive wave of new star formation that will light up the night sky with the glow of young, blue suns. The galactic center will become a place of transformation, where the old order of the two systems is dismantled to make way for the new. This starburst phase will consume the remaining gas reservoirs of both galaxies, lighting up the merging systems with the radiance of millions of newborns, creating a spectacular display of cosmic fireworks that will last for hundreds of millions of years, tracing out the boundaries of the new galaxy in lines of brilliant blue light and reorganizing the gas lanes. The vast spaces between the stars act as a shield, preventing physical impacts and ensuring the safety of individual solar systems during the transition. At the heart of this cosmic merger, the two supermassive black holes will begin a slow, gravitational dance. Andromeda harbors its own central giant, an object that is significantly larger than Sagittarius A, weighing between 100 million and 200 million times the mass of the Sun. As the two galaxies merge, these two massive black holes will sink toward the center of the new system, drawn inward by the gravitational drag of the surrounding stars. This process, known as dynamical friction, occurs as the massive black holes transfer their kinetic energy to the sea of stars through which they travel, throwing individual suns into new, wider orbits, while the giants sink deeper into the core. Over millions of years, they will form a binary pair, orbiting one another in a slowly tightening spiral. As they draw closer, their orbital speeds will accelerate, reaching significant fractions of the speed of light, their gravity warping the space-time around them with intense force. This binary phase is a crucial step in the merger process, where the two central giants are locked in a gravitational embrace that will gradually bring their event horizons together, shaping the future core of the united galaxy. This gravitational friction is a slow and steady process, transferring kinetic energy from the black holes to the wider stellar background and slowing down their orbits. In the final stages of the merger, the binary black holes will radiate their orbital energy away in the form of powerful, low-frequency gravitational waves. These ripples in the fabric of space-time will travel across the universe, carrying the signature of the collision to the most distant galaxies. Finally, the two horizons will touch, and the black holes will merge into a single, supermassive giant that will weigh over 150 million solar masses. This merger will release an amount of energy that is almost beyond calculation, distorting the local geometry of space and time before settling into a state of quiet equilibrium at the center of Milomeda. The release of gravitational waves during this final coalescence represents one of the most energetic events possible in the cosmos, a final chirp of space-time distortion that will announce the merger to the rest of the universe. The new supermassive black hole will act as the central anchor for the entire elliptical galaxy, its massive gravity holding the combined stellar population in a stable, rotating system that will endure for trillions of years, far into the deep future of the cosmos. The resulting single black hole will be one of the largest in our corner of the universe, a silent giant anchoring the new galaxy and guiding the stars. This future merger is linked to the life cycle of our own sun. 4.5 billion years is the approximate time remaining before the sun exhausts its nuclear fuel and swells into a red giant, engulfing the inner planets of the solar system. The collision of our galaxy therefore mirrors the timeline of our own world's end, connecting the destiny of Earth to the grand movements of the cosmos. It is a reminder that the structures we perceive as permanent, our planet, our sun, and our galaxy are all transient entities, subject to the cycles of birth, change, and rebirth that govern the universe. This synchronization of stellar and galactic lifetimes highlights the interconnectedness of the cosmos, showing that the fate of our local neighborhood is tied to the larger dynamical movements of the local group, proceeding in a slow, majestic progression that links the death of our star to the birth of a new galaxy. As our sun fades into a white dwarf, the surrounding stars of the Milky Way and Andromeda will merge, creating a new galactic home. This connection shows that our solar system is not isolated, but is part of the larger dynamical evolution of the local group, linking the smallest planetary scales to the largest galactic structures. The creation of Milomeda represents a transition rather than a simple destruction. The stars of the Milky Way and Andromeda will continue to shine, their paths organized into a new, larger structure that will remain stable for trillions of years. The merger of the two central black holes will create a new, quiet anchor for this stellar city, a single point of gravity around which the united populations of stars will dance. This slow, grand evolution is a testament to the order that underlies the apparent chaos of the universe, a quiet reorganization of matter that continues to unfold across the vast stretches of cosmic time, moving peacefully in the dark. The new elliptical galaxy will be a place of quiet starlight, dominated by old, stable stars that move in random, three-dimensional orbits, tracing out a giant stellar cloud that will slowly drift through the expanding universe, a peaceful monument to the two spiral galaxies that once occupied this corner of space, and continuing their slow, majestic dance long after the gas has been completely consumed, resting in the stillness of the infinite night. This giant elliptical galaxy will be a place of quiet starlight, where the merged populations of stars will orbit in peace and order, tracing out stable trajectories that will endure for eons, a monument to the organizing power of gravity, projecting into the ultimate future of the cosmos, far beyond the age of stars and the mergers of galaxies. The universe enters a quiet, final epoch, billions of years from now, when the last suns have exhausted their fuel and faded into white dwarfs and cold iron remnants. The only active structures remaining in the universe will be the supermassive black holes. In this distant era, known to cosmologists as the black hole era, the universe is cold and silent, a dark ocean where the only landmarks are these rotating giants. Yet, even these colossal structures, which once seemed to represent the ultimate symbols of permanence and destruction, are not destined to last forever. They are slowly, silently evaporating, returning their gathered mass back to the empty space from which it came, a slow dissolution that will eventually return the universe to a state of absolute, peaceful vacuum. This process of decay represents the final chapter in the life cycle of matter, where even the most dense and massive gravitational anchors are subject to the laws of quantum mechanics, slowly fading away over timescales that stretch the limits of human imagination. This long-term decay represents a fundamental feature of black hole thermodynamics, where even the most massive anchors slowly fade away, returning their energy back to the quantum fields that thread through the empty space. The process of this decay is governed by the laws of quantum mechanics, first described by the physicist Stephen Hawking in the decade of the 1970s. Hawking showed that empty space is not a complete void, but is filled with quantum fluctuations where virtual particle-antiparticle pairs constantly pop into existence and annihilate each other almost immediately. However, when these pairs appear right at the event horizon of a black hole, the intense gravity can separate them. One particle falls across the boundary, while the other escapes into the surrounding space. To an observer at a distance, it appears that the black hole has emitted a particle of thermal radiation. Because energy must be conserved, the energy for this emission is drawn from the mass of the black hole, causing it to lose weight. This quantum process represents a microscopic leak that slowly drains the black hole's energy, converting the massive gravitational potential of the core into a faint stream of thermal particles that escape into the surrounding space, showing that the event horizon is not an absolute wall, but is a permeable boundary where quantum effects can bypass the gravitational hold. This quantum process is a direct consequence of quantum field theory in curved spacetime, where the vacuum is not truly empty but is filled with fields that interact with gravity, creating a bridge between the large and small. For a black hole as massive as Sagittarius A, this rate of evaporation is incredibly slow. The temperature of its Hawking radiation is a tiny fraction of a degree above absolute zero, far colder than the temperature of the cosmic microwave background that currently fills the universe. As long as the black hole continues to absorb gas, dust, or even the faint light of distant stars, it will grow rather than shrink. But in the far future, when the expansion of the universe has pushed all matter away and the cosmic background has cooled to absolute nothingness, the evaporation will dominate. The timeline for Sagittarius A to dissolve completely is almost beyond human comprehension, requiring a number of years that can be written as a 1 followed by 85 zeros. This vast expanse of time is a testament to the stability of the central giant, showing that it will remain the anchor of our galactic remnants long after all starry light has been extinguished, a silent keeper of the galaxy's memory that will outlast the stars themselves, before finally returning its mass to the silent void in a final, quiet burst of thermal energy. This immense timeline is a reminder of the scale of the universe, where the most permanent structures are transient over long timescales, returning to the void. This slow evaporation introduces a profound puzzle known as the information paradox. In quantum physics, information about the quantum state of matter can never be destroyed. If a star, a planet, or even a simple atom falls into a black hole, the details of its composition must be preserved. But Hawking radiation is purely thermal, carrying no information about the material that fell in. If the black hole evaporates completely, leaving behind only a sea of random heat, the information seems to have been wiped from the universe, violating the core principles of quantum mechanics. This contradiction has challenged the minds of theoretical physicists for 50 years, representing a frontier where the physics of gravity and the physics of the very small collide. The paradox forces us to question our most basic assumptions about the nature of space, time, and physical laws, suggesting that either our understanding of gravity is incomplete or quantum mechanics must be modified to accommodate the extreme conditions that exist at the boundary of a supermassive black hole, where information is stretched and tested. The resolution of this paradox represents one of the primary goals of modern theoretical physics, uniting gravity and quantum mechanics in a single framework. Various solutions have been proposed to resolve this paradox. Some researchers suggest that the information is not lost, but is encoded in subtle quantum correlations within the radiation itself, carried away in a highly scrambled form. Others propose that the event horizon is not a simple, empty boundary, but is a structure that stores the information on its surface, projecting it back out as the black hole decays. To fully resolve the paradox requires a complete theory of quantum gravity, a framework that unites Albert Einstein's general relativity with the laws of quantum mechanics. The study of real black holes, even in their silent states, provides the constraints needed to guide the development of this unified theory. This intellectual quest connects the largest structures in the universe to the smallest quantum interactions, showing that the resolution of the information paradox will reshape our understanding of the entire cosmos, revealing the mathematical principles that govern both the collapse of stars and the quantum structure of space itself, and bringing a unified order to the physics of the universe. This search for a unified theory of quantum gravity is one of the grandest intellectual journeys in science, seeking the fundamental rules that coordinate the cosmos. The slow evaporation of Sagittarius A offers a perspective on the nature of impermanence in the cosmos. The central giant, which once anchored our galaxy and controlled the movements of billions of stars, will eventually dissolve, returning its mass to the universe as a gentle stream of light and heat. It is a reminder of the circularity of all things in the universe, where even the most permanent anchors are transient, slowly returning their energy back to the quiet void. The black holes will fade, the radiation will disperse, and the universe will return to a state of absolute, peaceful silence. A quiet dark, where the journey of matter and light is finally complete, resting in the stillness of the infinite night. This eventual decay is not a tragedy, but a peaceful return to the background state of the universe, where the boundaries of space and time dissolve, and the emptiness is once again quiet, holding the memory of all the stars that once danced in the dark, and resting in the absolute silence that preceded the birth of light. Sleeping in peace, this return to the vacuum is the final chapter in the story of space and time, a peaceful silence that completes the journey, leaving the universe in a state of absolute rest, where the memory of the starlight is preserved in the cold, silent dark. The long, majestic journey through the deep reaches of the galactic center now begins to quiet down and fade, and the mind is warmly invited to turn away from the extreme densities, the high-energy flares, and the massive gravitational fields that govern the heart of our galaxy. The scale of the cosmos is incredibly vast, yet it exists in a state of profound, absolute silence, where every movement of matter and light proceeds without a single sound. As we leave the crowded, brilliant core of the Milky Way behind us, we feel the density of the stars begin to thin out and scatter, returning gradually to the quiet, dark suburbs of our own solar neighborhood. The millions of suns that were once ablaze in the sky fade into a soft, distant glow, blending together into a quiet, shimmering path of silver starlight that stretches across the heavens like a silent road. The galaxy is slowly receding into the background, its massive spiral arms wrapping around the central giant in a slow, eternal embrace that has continued for billions of years and will continue long after our brief journey is complete. We are drifting peacefully through the calm, intergalactic spaces, where the emptiness is vast, cool, and welcoming, a silent ocean of darkness that holds the galaxies like lonely, quiet islands of starlight. There is no need to rush, and no need to remember the numbers, the complex science, or the massive structures we have witnessed tonight. Simply let the quietness of the void settle over the mind, allowing the thoughts of the day to dissolve into the absolute peace of the cosmic night. The universe is a place of deep, undisturbed rest, and we are floating in its quiet, slow-moving currents, resting in the stillness of the infinite dark. In this silent, empty space between the galaxies, the temperature of the void is cold, yet it is a peaceful, undisturbed coldness that brings a sense of absolute calm, safety, and quietness to the spirit. The high-energy cosmic rays, the twisted magnetic fields, and the superheated plasma accretion disks are now far away, reduced to tiny, insignificant whispers in the grand, limitless scale of the cosmos. The stars are distant pinpricks of silver light, scattered across the dark dome of space like diamonds on a soft velvet sheet, shining with a steady, quiet radiance that does not flicker, change, or demand attention. We are drifting through a near-perfect vacuum, far emptier than any nebula in the galactic plane, a space where there is no pressure, no gravity to pull us, and no light to disturb our vision. The emptiness itself has a presence, a soothing and protective depth that cradles the mind and allows any remaining tension in the shoulders to melt away completely. Let the stillness of this intergalactic void wash over the thoughts, breathing in the quietness of the space and breathing out any residual worries, plans, or cares of the waking world. The orbits of the stars proceed without our effort, the black holes spin without our awareness, and the universe continues its slow, majestic dance in the dark, completely independent of our human concerns. We are simply observers, resting in the absolute quiet of the cosmic night, surrendered to the peace of this infinite dark void, drifting deeper into the quiet. As we continue to drift, our attention is gently guided back toward our own home galaxy, back toward the outer suburbs, where a quiet yellow dwarf star hums in the darkness. This is our sun, a stable and comforting presence that has warmed our world for 4.5 billion years, guiding the paths of the planets in calm, circular orbits. The The solar system appears as a quiet sanctuary in the vastness of the cosmos, a place where the chaotic gravitational tugs of the galactic core are reduced to a distant, gentle memory. We watch the planets glide in their orbits, stable and secure, locked in a silent dance that has remained undisturbed for eons. The solar system is a safe harbor, protected by the magnetic field of the sun and the vast distances of empty space that separate us from the crowded core. The gentle gravitational bond of our sun keeps each planet in its secure, repeating path, providing a stable cradle for life. This stability is a quiet comfort, reminding us of the order that exists even in the deep reaches of space. As we approach our own planet, the blue sphere of Earth appears in the distance, wrapped in its soft, protective blanket of atmosphere that shields us from the cold void and the harsh radiation of the stars. It is a beautiful, fragile world, shining quietly in the dark, a testament to the capacity of the universe to create environments of comfort, stability, and peace. We are returning home, letting the mind settle into the familiar, gentle rhythms of our own world, feeling the comfort of returning to the place where we belong. Approaching the night side of Earth, the landscapes below are bathed in a soft, quiet darkness, where the bustle of the day has faded into the peace of the evening. The cities are silent, their lights glowing like distant stars scattered across the continents, while the deep oceans reflect the quiet light of the moon. The wind rustles gently through the trees of quiet forests, and the waves lap softly against the shores of quiet beaches, creating a natural, repeating rhythm that mirrors our own quiet breathing. The air is cool and fresh, carrying the scent of damp earth and night-blooming flowers, inviting the body to rest and release any remaining energy. The stars above continue their silent watch, casting a soft, gentle radiance over the sleeping world. The night is a time of healing, a quiet interval where the energy of the day is restored in the cool dark. The weight of the day has been lifted, and the responsibilities of the waking world are now far behind us, replaced by the simple, comforting presence of the dark. We are safe, resting in our own rooms, protected by the solid ground beneath us and the quiet sky above. The universe is vast and mysterious, yet it is also our home, a place where we belong and where we can find absolute rest. Let the quiet darkness of the night envelop the mind, letting the thoughts drift into the peaceful, silent spaces of sleep, wrapping us in a cocoon of safety. As the body settles into a comfortable position, let the breathing fall into a natural, effortless rhythm, matching the slow, steady pulse of the cosmos. Inhale the quiet, cool air of the night, letting it fill the lungs with a sense of peace, and exhale slowly, releasing any remaining tightness or thoughts from the mind. With every breath, the body becomes slightly heavier, sinking deeper into the soft support of the bed, while the mind becomes lighter, drifting like a particle of dust in a beam of starlight. There is nothing more to see, nothing more to do, and nowhere else to go tonight. The journey through the galactic center is complete, and the stars will continue to shine without our watchfulness. The supermassive gravity of Sagittarius A, the S stars zipping in their orbits, the G objects in their dusty cocoons, and the Fermi Bubbles rising like monuments in the dark are all part of a grand, orderly system that proceeds in perfect harmony, a cosmic clockwork that is stable and secure. We can let go of our need to understand, our need to remember, and simply trust the order of the universe, allowing ourselves to be carried by the gentle currents of the night into a state of deep, undisturbed rest, floating away on the waves of stillness. Let the mind float away on the quiet sea of stillness, leaving all concerns behind. Feel the slow, repeating rhythm of your chest rising and falling, a gentle wave that connects you to the natural rhythms of our home world. The light is fading now, the stars are growing dim, and the silent dark of the cosmos is expanding, bringing a profound sense of comfort, safety, and peace. The mind drifts farther and farther away from the words and the science, entering a quiet, warm space where thoughts are soft and slow, like clouds drifting across a night sky. The universe is silent, the galaxy is quiet, and the room is still, all bound together in a single, peaceful moment of rest. Let the silence of the galactic core, the deep quiet of the intergalactic void, and the gentle darkness of the night guide the spirit into a deep, restoring sleep that will refresh the body and soothe the mind. The journey is over, the path is clear, and the absolute peace of the infinite night is ours to keep, cradling the body in a warm, protective embrace that will last until the morning light. As the voice fades away, let the silence of the room become a warm, protective blanket that wraps around you. Sleep is a natural, peaceful state, and you are drifting into its comfortable depths, resting in the quiet. Sleep now, letting the soft voice fade into the silence of the room, letting the starlight guide the dreams, and resting in the knowledge that we are a part of this vast, beautiful, and orderly cosmos, floating quietly in the dark, sleeping in peace, drifting into the absolute quiet of the night. Is greater than is greater than is greater than.